Hi students, the final video for this series. In this video we're going to look at the 2023 HSC Extension 2 Maths paper solutions, questions 14, 15 and 16. Question 14a, let z be the complex number e to the I pi on 6 and w be the complex number e to the 3I pi on 4. Part 1, by first writing z and w in Cartesian form or otherwise show that the modulus of z plus w all squared is equal to 4 minus root 6 plus root 2 all over 2. Okay, so we're going to start by writing in Cartesian form. So z is equal to, you can see it's got a modulus of 1, so it's going to be cos pi on 6 plus I sine pi on 6, which is equal to root 3 on 2 plus I over 2. And then w will equal, again a modulus of 1, cos 3 pi on 4 plus I sine 3 pi on 4, which is equal to negative root 2 on 2 plus I root 2 on 2. And so z plus w will equal root 3 on 2 minus root 2 on 2 plus I a half plus root 2 on 2. And so the modulus of z plus w all squared will be root 3 minus root 2 on 2 all squared plus 1 plus root 2 all over 2 squared, which is equal to 3 minus 2 root 6 plus 2 all over 4 plus 1 plus 2 root 2 plus 2 all over 4, which is equal to 3 plus 1 is 4 plus 2 is 8 minus 2 root 6 plus 2 root 2 all over 4, and cancelling we are going to end up with 4 take away root 6 plus root 2 all over 2 as required. 2. The complex numbers z, w and z plus w are represented in the complex plane by the vectors OA, OB and OC. O is the origin, show that the angle AOC is 7 pi on 24. Alright, we need to draw a diagram here. So we're going to have z coming out here roughly, and that is pi on 6. And then we've got w coming up here, and that is 3 pi on 4. And then of course we have got z plus w coming through here. And so this is A, that's O, this is B, and this up the top is C. And we want to work out the angle AOC, so this angle here. If you can see it, right. And we're just going to use properties of a parallelogram actually. So we know that if that is 3 pi on 4, that one there must be pi on 4. And so angle BOA must be pi, take pi on 4, take pi on 6, which is equal to 12, let's see, we've got 12 pi take 3 pi take 2 pi, getting there, it's equal to 12 take 3 is 7 pi on 12. And through the properties, this is a show that question, so this is a parallelogram, so we know that OA will bisect angle BOA, therefore angle COA will equal 7 pi on 24. Part 3. Deduce that cos 7 pi on 24 is equal to this. Alright, this is going to come from this triangle here. Now we know the length of OA is 1, and the length of OB is also 1, which makes CA, but has length 1 as well. And we just worked out this length here. It is there. And we know that this angle here is 7 pi on 24. So we're just going to use the cosine rule. So cos 7 pi on 24 will equal 1 squared plus this guy squared, which is 4 minus root 6 plus root 2 on 2, take away 1 squared, all over 2 times 1 times the square root of 4 minus root 6 plus root 2 all over 2, which is equal to 1 take 1, that's gone, and we've got 4 minus root 6 plus root 2 all over, that 2 is going to fall down there, so 4 square root, I'm going to run out of room, 4 take root 6 plus root 2, and I've got a square root of 2 there that is going to come up the top, which is equal to, now I can cancel this square root with part of this numerator. It's going to become a square root on top. Hopefully that makes sense to you. Now let's put this root 2 inside this square root, which is going to give us square root of 8 take 2 root 6 plus 2 root 2 all over 4 as required. 14b. Point P is 4 meters to the right of the origin O on a straight line. A particle is released from rest at P, so T is equal to 0, X is equal to 4, and V is equal to 0. Moves along the straight line in simple harmonic motion about O with period 8 pi seconds. So we know that's equal to 2 pi on n. N must be equal to 1/4. After 2 pi seconds, another particle is released from rest at P and also moves along a straight line in simple harmonic motion about O with period 8 pi seconds, so same period. Find when and where the two particles first collide. All right, so we know this is in simple harmonic motion about O, but we don't know what the amplitude is. We're assuming it's 4, but I'm just going to do a quick check. We'll use V squared is equal to N squared A squared minus X squared. So at T is equal to 0, V is equal to 0, N is equal to 1/4, A we don't know, and X is equal to 4. And so that's going to give us A squared minus 16 is equal to 0. A, which is the amplitude, is equal to 4. So that's nice. It means that we can write the equation of motion. So it's starting up here, we're going to use cos, and it's going to have an amplitude of 4. It's going to be cos nt, so 1/4 t. All right, now let's look at the other particle. So our first particle, let's do a colour for it. It's going like this. And then our second particle, after 2 pi seconds, this particle is sitting here. It's released. Let's do green. And it does the same thing, basically. All right, let's draw this out. Do this, but anyway, let's try. Here's P. We'll call this Q, and they're 4 and -4. So our first particle moves, and then when it gets to O, the second particle starts. So at this point here, the new particle starts. And then we go another 2 pi, and this particle at that point would have moved this far. And then it's turning, and it's only going to get halfway back before these two meet. So what's that? 2, 4, 5 pi. So they're going to meet at t is equal to 5 pi. And now all we've got to do is substitute that into our equation. X is equal to 4 cos 5 pi on 4, I don't know why I did a bracket there, is equal to 4 lots of cos 5 pi on 4, that's down in here, so it's cos pi on 4 is root 2 on 2, negative root 2 on 2, which is negative 2 root 2, which of course, yeah, it would be negative. So that's where it meets. Do we have any units? We've got seconds, 4 meters. So meters and seconds. Question 14c. A projectile of mass m kilograms is launched vertically upwards from the origin with an initial speed of v0. The acceleration due to gravity is g, meters per second squared. The projectile experiences a resistive force of magnitude kmv squared newtons, where k is a positive constant and v is the speed of the projectile at time t seconds. Part 1, the maximum height reached by the particle is h meters. Show this. All right, let's start with F is equal to ma, which on the way up is going to be equal to negative mg take away kmv squared. And we can cancel all of those m's out and we end up with A is equal to negative g take away kv squared. We are wanting to work out the maximum height, which means we need x. So we're going to do v dv dx, which is equal to negative g take away kv squared, divide both sides by v, and then invert both sides, so dx dv will equal negative v over g plus kv squared, which means that x will equal negative integral of v over g plus kv squared dv. All right, we've got a log here, base e, and we have the reverse chain rule. When we find the derivative of this, we get 2kv, so I'm going to need 2kv on the numerator. Let's adjust it with 1 over 2k out the front. Is equal to negative 1 on 2k ln g plus kv squared plus c. Now, initially, p is equal to 0, we don't care, x is equal to 0, and v is equal to v naught, which means that 0 will equal negative 1 on 2k ln g plus kv naught squared plus c. Therefore, c is equal to 1 on 2k ln g plus kv naught squared. And so x is going to be equal to negative 1 on 2k ln g plus kv squared all over g plus kv naught squared. All right, we want to work out the maximum height. That, of course, is when the particle turns, and v is going to be equal to 0. And so the maximum height will be h, which will be equal to negative 1 on 2k ln g over g plus kv naught squared. I've got it upside down, don't I? So let's flip it. 1 on 2k ln g plus kv naught squared all over g. Part 2. When the projectile lands on the ground, its speed is v1 meters per second. v1 is less than the magnitude of the terminal velocity. Show this. So this was the model for the projectile when it was going up. When it's coming down, it is going with gravity, but it still is against that air resistance, okay, mv squared. So we need to set up a new model, which is going to be F equals ma, which is going to be equal to mg minus kmv squared. And again, we can say A is equal to G minus km, nope, no m, v squared. And again, we're talking about x, aren't we? So we want v dv dx, which is going to be equal to G minus kv squared, and divide both sides by the v. So we end up with dx over dv is equal to v over G minus kv squared, which means that x is equal to the integral of v over G minus kv squared dv. Now again, we've got log base e, and the derivative of this is negative 2kv, so that's what we need at the top. And adjusting, we get this is equal to negative 1 over 2k ln G minus kv squared plus c. So now we need to substitute in initial conditions. Now remember, we've started a new system here. We're up the top, and downwards is positive. Here we have t is equal to 0. We'll say x is equal to 0 and v is equal to 0. And so 0 is equal to negative 1 on 2k ln G plus c. Therefore, c is equal to 1 on 2k ln G, which means that x is going to be equal to negative 1 on 2k ln G minus kv squared on G. Okay, now when the projectile lands on the ground, which is going to be when x is equal to h, the speed is v1. So let's substitute that in. So x is 1 on 2k ln kv naught squared plus g over g, and it's going to be equal to negative 1 on 2k ln g minus kv1 squared on g. And so these parts cancel out. I've got a negative here, which is pesky. I'm just going to invert this and get rid of it. We have kv naught squared plus g all over g is equal to g over g minus kv1 squared. What's multiplying? Kv naught squared plus g multiplied by g minus kv1 squared is equal to g squared. Expanding, kv naught squared g minus k squared. Yep, v naught squared v1 squared plus g squared minus kg v1 squared is equal to g squared. Alright, they will cancel. And we want this guy to go to the other side, so we've got kv naught squared g minus kg v1 squared is equal to k squared v naught squared v1 squared. One of those k's will cancel out, and factorising we get g brackets v naught squared minus v1 squared is equal to k v naught squared v1 squared. Question 15a, part 1. Let Jn equal the integral between 0 and pi on 2 of sine to the power of n theta d theta, n greater than or equal to 0 as an integer. Show that Jn is equal to n minus 1 all over n, Jn minus 2 for all integers, n greater than or equal to 2. Alright, we'll start off by splitting out a sine theta from sine to the power of n theta. And then we're going to use integration by parts. So we have got u is equal to sine to the power of n minus 1 theta, and u dashed will be n minus 1 sine n minus 2 theta multiplied by cos theta, and then v dashed will be equal to sine theta, and so v will equal negative cos theta. Okay, Jn is equal to u times v. Our limits are 0 and pi on 2. Take away u dashed times v, which is negative cos, so that's make that a plus, and this will be cos squared d theta equals. Now, when I substitute pi on 2 in, I get 0, and when I substitute 0 in, I get 0, so that's all gone. So that leaves me with n minus 1, the integral of sine to the power of n minus 2 theta times cos squared theta d theta, which is equal to n minus 1 integral between 0 and pi on 2 sine to the power of n minus 2 theta 1 minus sine squared theta d theta, which equals n minus 1 integral between 0 and pi on 2 sine to the power of n minus 2 theta take sine to the power of n theta d theta, which is equal to n minus 1, and then we have got j n minus 2 take j n. And now let's just collect these terms together. So we've got jn is equal to n minus 1 jn minus 2, take away n minus 1 lots of jn, so jn 1 plus n minus 1 is equal to n minus 1 jn minus 2. Njn is equal to n minus 1 multiplied by jn minus 2, and jn is equal to n minus 1 on n jn minus 2. Part 2, let In equal the integral between 0 and 1 of x to the power of n, 1 minus x to the power of n dx, n is a positive integer. By using the substitution x equals sine squared theta, or otherwise show this. Alright, so In is going to be equal to the integral of sine squared theta to the power of n, 1 minus sine squared theta to the power of n, and now we need to work out a couple of things. If x is equal to sine squared theta, then dx is equal to 2 sine theta cos theta d theta. Let's do the limits. When x is equal to 0, theta is equal to 0, and when x is equal to 1, theta is equal to pi on 2. So we're going to multiply it by 2 sine theta cos theta d theta, and our limits are 0 to pi on 2. Let's tidy that up. We've got the integral between 0 and pi on 2 of 2 sine to the power of 2n plus 1 theta multiplied by cos to the power of 2n plus 1 theta d theta. And this is nice, isn't it? Because it's equal to the integral between 0 and pi on 2, and then we've got sine theta cos theta to the power of 2n plus 1 d theta. And so what I want to do is change this into sine 2 theta. And to do that, we are going to need a 2 here, and then we'll have to adjust it. If that makes sense. I'm just going to get rid of that guy. All right, so it's equal to integral between 0 and pi on 2 of 2. And there I have got sine 2 theta to the power of 2n plus 1, and divided by 2 to the power of 2n plus 1 d theta is equal to 1 over 2 to the power of 2n integral between 0 and pi on 2 of sine to the power of 2n plus 1 2 theta d theta. Now, this is quite a nasty question because a lot of students would have got to this point and looked at what they're trying to prove and thought, well, I've nearly got it except for this theta here. We've got 2 theta. And they probably went and did it again and got the same answer. And then they probably assumed that the question is wrong, and it isn't. The HSC is never wrong. So the other clue that we've got that we need to do a bit more work is this 4 here. We've really only done 3 marks worth of work, so we need to keep going. We're going to make a substitution. Let u equal 2 theta, and that means du is equal to 2 d theta, and when theta is equal to 0, u is equal to 0, and when theta is equal to pi on 2, u is equal to pi. Okay, let's make that substitution. In is going to be equal to 1 over 2 to the power of 2n, integral between 0 and pi of sine to the power of 2n plus 1 theta, and instead of d theta we will have du divided by 2, which equals 1 over 2 to the power of 2n plus 1 integral between 0 and pi of sine to the power of 2n plus 1 theta d theta. And we're still not there, are we? So now we need to just think about this, and in particular the graph of it. So normal sine is symmetrical, remember? And this part here is symmetrical about the line pi on 2. In other words, the area under the curve between 0 and pi on 2 of any sine curve is going to be, 2 lots of that, is going to be equal to the integral between 0 and pi of sine theta d theta. And it's the same for sine to the power of 2n plus 1. So this is equal to 1 over 2 to the power of 2, 2n plus 1, and instead of this we're going to have 2 lots of the integral between 0 and pi on 2 of sine to the power of 2n plus 1 theta d theta, and just resolving this part here we have the answer. It's 1 over 2 to the power of 2n integral between 0 and pi on 2 sine to the power of 2n plus 1 theta d theta. What a horrible question. 3. Hence or otherwise show that In is equal to n over 4n plus 2 multiplied by In minus 1. Now, this is what we proved in part 1, which we haven't used so far, and this is what we just proved. So let's start with In is equal to 1 over 2 to the power of 2n, and that part there is j 2n plus 1. So this is equal to 1 over 2 to the power of 2n, and now let's use this relationship here. So it's going to be equal to 2n plus 1 minus 1 over 2n plus 1 j 2n plus 1 minus 2. Tidying that up, 1 over 2 to the power of 2n multiplied by 2n over 2n plus 1 j 2n minus 1. Now looking at where we've got to get, we don't want a j 2n minus 1, we want an I n minus 1. So let's start again with what we started with at the beginning. In is equal to 1 over 2 to the power of 2n j 2n plus 1. And let's form In minus 1, which is equal to 1 over 2 to the power of 2 lots of n minus 1 j 2n minus 1 plus 1 is equal to 1 over 2 to the power of 2 brackets n minus 1 j, this is 2n minus 2 plus 1, which is 2n minus 1. And we're just going to make this substitution. Let's make j 2n minus 1 the subject. And we're going to have 2 to the power of 2 brackets n minus 1 I n minus 1. is equal to 1 over 2 to the power of 2n times 2n over 2n plus 1 multiplied by 2 to the power of 2 brackets n minus 1 I n minus 1 equals, wow, what a mess. Let's just rewrite that bit there. What have we got? That's 2 to the 2n divided by 2 squared. So that cancels out. Oops, all of that. And we're going to end up with, well, one of those cancels out as well. N over 2 lots of 2n plus 1 multiplied by I n minus 1, which is correct. 15b, on the triangular pyramid ABCD, L is the midpoint of AB, M is the midpoint of AC, N is the midpoint of AD, and P is the midpoint of CD, Q is the midpoint of BD, and R is the midpoint of BC. Let the vector AB be represented by B, so that's here. Let the vector AC be represented by C, and let the vector AD be represented by D. Show that LP, which is here, is equal to a half multiplied by negative B plus C plus D. Okay, so if we want LP, then what we can do is go here and then from A through to P. In other words, LP is equal to LA plus AP. And we know that LA is equal to negative a half lots of B. And AP is here. That's the midpoint. I'm running out of colours here. I'm just going to get rid of a little bit. Is the midpoint of AC and AD. So in other words, it's equal to a half of D plus C, which means it's equal to a half negative B plus D plus C. Part 2, it can be shown similar equations for MQ and NR. We are required to prove this. So it's easier to start with the right-hand side, and it is equal to 4 lots of. So LP, we proved that just before, so we want the modulus of a half negative B plus C plus D all squared plus a half from here, B minus C plus D squared, and then a half, what do we got here, B plus C minus D. Okay, it's going to be equal to 4 lots of. Now remember that the modulus of A, for example, all squared is equal to A dot A. So we're going to have a quarter, that's nice, negative B plus C plus D dot negative B plus C plus D plus a quarter, B minus C plus D dot B minus C plus D plus a quarter, B plus C minus D dot B plus C minus D. Now obviously we can cancel this 4 and all of these quarters. And now we have to expand all of these dot products. Now this is just too boring to do on video. You'd be listening to me going B dot C and D dot D and blah blah blah. So I've already done it. It's still horrendous, isn't it? Okay, so we've got 3 lots of mod B squared and 3 lots of mod C squared and 3 lots of mod D squared, and then we can cancel. So minus b dot c, and there's a plus somewhere down here, there, minus b dot d plus minus c dot b there, plus cd minus d dot b and dc there. Okay, and that leaves us with two lots of b dot c. Actually, it's negative, my apologies. And I'm trying to find the rest of it here. Minus two lots of b dot d and minus two lots of c dot d. Now at this point, it seriously is easier to start from the left-hand side and then work towards the middle. However, that is a bit of a no-no with proof, but we can use the same technique just to try and get there. So the thing that's missing from our right-hand side is this part here. So let's have a look at the diagram and see where that comes from. So mod BC all squared, well, that's the same. Let's have a look at BC. It's here. It's the same as mod C take B all squared, or the dot product C take B with itself. And similarly, BD, where's BD? BD is D take away B dot D take away B, and what's the other one? CD. CD is D take away C dot D take away C. And so to use that, we're just going to write in the middle of our proof, but, and then state these equations. And let's expand them all out. Again, I've just done that beforehand. Now, can you see that, for example, we've got 3 mod b squared here, and in these equations, I've got 1, 2 of them. So I'm going to have 1 left over. So let's go back into our proof and write, therefore, right-hand side is equal to mod b all squared plus mod c all squared plus mod d all squared. And then I'm going to rewrite all of these because it will be equivalent. So plus c take 2c b plus c squared, which is equal to b is AB, c is AC, and d is AD, and then we proved all the rest of it before. Equals left-hand side. 15c, curve L spirals 3 times around the sphere centered at the origin and with radius 3 shown. A particle is initially at the point 0, 0, negative 3 and moves along the curve L on the surface of the sphere ending at the point 0, 0, 3. By using the diagram below, which shows the graphs of the functions f of x equals cos pi x and g of x equals the square root of 9 minus x squared, and considering the graph of y equals f of x multiplied by g of x, give a possible set of parametric equations that describe the curve L. Okay, let's see whether we can graph the curve y is equal to cos pi x multiplied by the square root of 9 minus x squared. So using our principles, this is from extension 1, we're going to look at critical points on this graph here. So firstly, we're looking for any zeros. So there's one there, and there's one here, and here, and here, and here, and here, and here, and here. So all of those points, the graph that we're going to draw is going to be equal to 0. So here, and here, 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 and these are just rough, obviously. Okay, now we're going to look at places where either one of these graphs is equal to 1. And so that's here, and here, and here. So let's do some multiplication. So at this point here, we're going to have 1 times that point there. So that's, when's that? -2, that's here, and it's a little bit above 2, that's about there. This one here, we've got 1 times 3, that's nice. Here, we've got the same situation as before, so that's going to be at 2 and approximately here. We've also got some negatives, negative ones. That one's not important because that was multiplied by 0. This one and this one here, so at -1. So at -1 times that point, so that's about here and here and there. And joining those points together, we're going to get something that looks roughly like this. Pretty hard to do on a computer screen. Now to get our parametric equations, we're going to squish this graph onto the z-x plane, and we'll get something that looks like this. So this is z, and this is x. So it starts down here at -3, and it goes like this. Up to there, roughly. And it looks really similar to this graph, except that this is z and this is x. So we can say that x is going to be equal to cos pi z times by the square root of 9 minus z squared. But we're going to let z equal t, and so x will equal cos pi t square root of 9 minus t squared. So we've got two of them, we just need y. We're going to do the same thing, we're going to squish the graph, but this time onto the yz plane. And the graph's going to look like this. It's going to be similar, but subtly different. Three and -3. So you're probably thinking, hopefully you're thinking, well, that's not cos, it's sine, and you are correct. Y is indeed equal to sine pi t square root of 9 minus t squared. But before we sign off on this question, we should check one thing. Is it going to be positive sine or negative sine? And the easiest way to do this is just to check a point. So I'm going to pick, remember this is t here, I'm going to pick, say, a half, and I'm looking for a negative value for y. So when I substitute it in, I'm going to get sine of pi on 2, square root of 9, take away a quarter. Well, that's positive, and so is that. This is positive. And so y is going to be equal to negative sine of pi on t square root of 9 minus t squared. 16a, let w be the complex number e to the 2i pi on 3. Part 1, show that 1 plus w squared is equal to 0. Nice easy question to begin with. We know that w cubed must be equal to 1 because e to the 2i pi on 3 cubed is equal to e to the 2 pi I, which is equal to 1. Therefore, w cubed minus 1 is equal to 0. Therefore, w minus 1, in brackets, w squared plus w plus 1 is equal to 0. Therefore, w squared plus w plus 1 is equal to 0. The vertices of a triangle can be labelled A, B and C in anti-clockwise or clockwise direction as shown. Three complex numbers A, B and C are represented in the complex plane by the points A, B and C respectively. Part 2, show that if triangle ABC is anti-clockwise and equilateral, then A plus BW plus CW squared is equal to 0. I quite like this question because this is a rotator of complex numbers in the complex plane, and it rotates it anti-clockwise by 2 pi on 3, and it doesn't change the magnitude because the magnitude of W is 1. So we're going to take this complex number, which is C minus A, rotate it by 120 degrees, which is this much, and it will become this here, which is A minus B. Hopefully that makes sense to you. So we have C minus A. We're going to rotate it by by 2 pi on 3, which means multiply it by e to the 2i pi on 3, and it will equal A minus B, which of course is C minus A W and equals A minus B. Let's expand that out. CW take AW is equal to A minus B, and let's get those A's together. AW plus A is equal to CW plus B, which means that A in brackets W plus 1 is equal to CW plus B, and we proved in part 1 that 1 plus W squared is equal to 0, and so 1 plus W must equal negative W squared. Or AW squared plus CW plus B is equal to 0. Multiply everything by W, we get AW cubed plus CW squared plus BW is equal to 0, but W cubed is equal to 1. Therefore, A plus CW squared plus BW is equal to 0. 3. It can be shown that if triangle ABC is clockwise and equilateral, then A plus BW squared plus CW is equal to 0. Show that if ABC is an equilateral triangle, then A squared plus B squared plus C squared is equal to AB plus BC plus CA. All right, now if ABC is an equilateral triangle, it can be traversed either clockwise or anti-clockwise, it doesn't matter. So both of these statements are true, which means that A plus BW squared plus CW multiplied by A plus BW plus CW squared must be equal to 0. And expanding that out, we get A squared plus ABW plus ACW squared plus ABW squared plus B squared W to the power of 4 plus BCW, sorry, that one's cubed there. My apologies. There. Plus BCW to the power of 4, yep, plus ACW plus BCW squared plus C squared W cubed is equal to 0. But W to the power of 4 is equal to W, and W cubed is equal to 1. So that means that A squared plus ABW plus ACW squared plus ABW squared plus B squared plus BCW plus ACW plus BCW squared plus C squared is equal to 0. All right, so A squared plus B squared plus C squared plus, let's collect these ABs together, and the ACs, and the BCs. Now since 1 plus w squared is equal to 0, which of course means that w plus w squared is equal to -1, then a squared plus b squared plus c squared minus ab minus ac minus bc must be equal to 0. And so a squared plus b squared plus c squared is equal to ab plus bc plus ca. 16b, prove that x is greater than ln x for x is greater than 0. Let's have a look at a sketch. Here's y equals x. Here's y equals ln x. So it looks like it's true. Now we've got two cases, I suppose. We've got what happens between 0 and 1, and then we've got what's happening x is greater than or equal to 1. So this one first. In between 0 and 1, x is greater than 0. You can see that from the graph. But ln x is less than 0. So in this particular domain, x is greater than ln x. Now for this, we're going to define a new function, f of x is equal to x minus ln x. And f of 1 is equal to 1 take away 0, which is equal to 1. Now, if we can prove that this function starts at 1 and then is increasing for x is greater than or equal to 1, then this whole thing here must be greater than 0. So let's do the derivative. It is equal to 1 take away 1 on x, which is equal to x take 1 on x, which is greater than 0. So since f of 1 is equal to 1 and f of x is always increasing, then, it says then, x minus ln x is greater than 0, therefore x is greater than ln x. Part 2. Using part 1 or otherwise, prove that for all positive integers n, e to the n squared plus n is greater than n factorial or squared. So we're going to use induction. We're going to prove it true for n is equal to 1. Left-hand side is equal to e squared. Right-hand side is equal to 1 factorial or squared, which is equal to 1. E squared is greater than 1, therefore true for n is equal to 1. Now we're going to assume it true for n is equal to k. In other words, e to the k squared plus k is greater than k factorial or squared. And now we want to prove it true for n equals k plus 1. So we are required to prove that e to the k plus 1 all squared plus k plus 1 is greater than k plus 1 factorial squared. So let's begin. We'll start here. E to the k squared plus 2k plus 1 plus k plus 1 is equal to, now I want to match this, e to the k squared plus k, what are we left with here, times e to the 2k plus 2. Now we know from our assumption that this is going to be greater than k factorial or squared multiplied by e to the 2k plus 2 by assumption. Which is equal to k factorial all squared e to the k plus 1 all squared. Now returning to part 1 for a minute, we proved that n is greater than ln n. And that's the same as e to the power of n is greater than n because n is positive. And looking at what we have here, e to the k plus 1 must be greater than k plus 1. And because everything's positive there, e to the k plus 1 all squared must be greater than k plus 1 all squared. So this is greater than k factorial all squared, k plus 1 all squared, which is equal to k plus 1 factorial all squared, as we were required to prove. So therefore, by the principle of mathematical induction, true for all n. Last question. 16c, the complex numbers w and z both have modulus 1, and pi on 2 is less than the argument of z divided by w, which is less than pi. Arg denotes the principal argument. For real numbers x and y, consider the complex number xz plus yw all over z. On an xy plane, clearly sketch the region that contains all points x and y for which pi on 2 is less than the argument of xz plus yw all over z and has less than pi. Let's start by drawing a diagram. Now remember that arg of z over w is equal to arg z take arg w. Both z and w lie in the unit circle because they've got modulus 1. So suppose w is here and z is out here. This is telling us that the angle between them, let's make that theta, is obtuse. Now let's have a look at this. xz plus yw over z, well that's equal to x plus y lots of w on z. And look, we've got the inversion of what we had before. So similarly, arg of w over z is equal to arg w take arg z, and it's pretty easy to see that arg w take arg z would be equal to negative theta. Okay, let's draw a new diagram. So now let's look at z on w. We know that its argument is an obtuse angle, and so it's in the second quadrant. So we'll put it up here. It also lies on the unit circle because z and w both have a modulus 1. And then this guy here, he's down here in the third quadrant. W on z also lies on the unit circle. This one here, we're told to sketch everything for where this is obtuse. So that also lies in the second quadrant, but not necessarily on the unit circle. So this is x plus y w on z. Now it's fairly obvious that y is going to have to be less than 0 because this lies down here in the third quadrant, it's negative. So the only way for this to lie in the second quadrant and for the imaginary part to be positive would be for y to be less than 0. We also know that the real part of x plus y multiplied by w on z must be less than 0 because we're in the second quadrant. Now we know the real part of w over z is equal to cos of negative theta. Cos is even, so that's equal to cos theta. And so x plus y times cos theta must be less than 0. Y cos theta is less than negative x. And now I want to divide both sides by cos, but is cos positive or negative? Remember, theta is obtuse, and cos of an obtuse angle is negative. So I am going to flip the sign. So I'm going to go y is greater than negative sec theta x. Okay, now there are some restrictions on this. So remember that theta is obtuse, so let's just do a quick graph. Here's a negative cos. We are in the second quadrant, and negative sec will look like that. So negative sec theta is greater than 1. So I'm just going to replace that negative sec with just k. So y is greater than kx, but k k is going to be greater than 1. So let's sketch it. So this line y equals kx, here's y equals x. It's going to be greater than that line, so it's going to be in here. But that line can get steeper and steeper and steeper. So it can go like this and like this. So it's actually going to be everything in this quadrant, not including this axis because y has to be less than 0, and not including this axis and not including the origin.